Hi, welcome back to chemistry, and we are looking at chapter 2, focusing on measurements and calculations. Obviously, chemistry, we're going to be taking a lot of measurements. We're going to be collecting a lot of data. We're going to be using those measurements to make calculations, and then from those calculations, we're going to draw certain conclusions. So, a big process in any science. So, as we jump into chapter 2 here, just a little preview of what we're going to be talking on, what we're talking about. Scientific method here in section 1. And really, scientific method is something that we do, I think, naturally. I think it's a part of our nature, how we're designed. We'll talk about that. Units of measure, so we're talking about predominantly the SI units. And then using those measurements. What good are they if we don't know how to use them? So, if you haven't already, you want to make sure that you're answering these previous concept questions. You can pause the video right now and take care of that, and then I'll check them when you submit this assignment. First section of chapter 2, we're looking at the scientific method. Now, it is technically defined as a logical approach to solving problems, and there's kind of a step process that most people would agree make up the scientific method. So you're going to be collecting data, you're going to be forming different hypotheses, you're going to be testing those hypotheses, you're going to be coming up with some conclusions, maybe some theories. If those theories stand the test of time, they might turn into laws. All of it is supported by data, though. Okay? That data may be observations, you may be using your senses, you may be actually measuring something, but it is largely based upon data, and from that data we are going to draw certain conclusions, make certain inferences. So, as I mentioned already, really I believe that it's a certain way that you've been designed. This is somewhat innate in all of us, that we do follow a particular method when we want to draw certain conclusions. So it's not something that you have to conjure up, it's just something that you have to tap into. Alright, those observations that we make, obviously we're going to be taking some different measurements and collecting data, and then we use that data in order to look at relationships. When we look at our 5 senses, obviously, sight, hearing, touch, taste, or smell, to obtain information. And then that information can be broken down into qualitative observations. Those are more descriptive in nature. Something, a certain color, or how something feels. And then there's also the quantitative observations that we make. Those are more measurement specific, numerical data. So something that you may weigh or find the length of, some value that you collect from a particular measurement. Okay? Also, we are going to be spending a lot of time interpreting graphs and making graphs. So graphs are a great way to show relationships. You can see a graph right here as certain data was collected, and then it was put into a nice organizational chart called a graph. All right? As we look at different lab experiments, you're going to be collecting different information, different values, different data. They're going to be controlled conditions, and that means those are the conditions that you want to try to keep steady and keep constant and not have them change, so you can focus on certain things and find the relationship between those certain things. Alright, this is just a term here, a system. When we talk about a system, we're talking about a particular region or sample of matter that you are focusing your attention on. So it is a specific portion of matter in a given region of space that has been selected to study. Okay? That's called a system. You're focusing on a particular, the matter in a particular container. Whatever's inside the container is a system. Everything outside of that would be called the surroundings. All right? Closed system just means that we are containing the matter and it's not going to be able to escape. Hypotheses, basically it's a statement that we're saying, here's something that I want to be able to test. Here's something that I think is going to play out. and I want to be able to test that to see if my statement is true or not. We want to find those relationships and patterns based upon our observations and the data that we collect. All right. Once you have kind of collected and analyzed data and you find relationships, you might want to begin to draw some type of conclusion from that. You might even want to start with a hypothesis first, something that you think is testable, and then use your experiment to test that. All right? You might write your hypothesis as an if-then statement, and if something is going to take place, then you think something else is going to result. There's a cause and effect. All right, so just be aware of that. Some other things that you need to be aware of in experiments that we're going to perform, as I mentioned already, controls. So if you have a control, that control is not going to change. Variables obviously are going to alter. They're going to alter their values based upon the conditions of the experiment. Make sure you understand what we mean by controls and variables. All right, you can pause here and just answer reading check question number 2, and then rejoin me. We like to, because in chemistry you can't see what is necessarily happening at the atomic level or the molecular level, we like to have models to try to represent what is taking place. So anytime we have a diagram or a structure or even information sometimes, a data table, that's a model that we can use to then try to formulate some type of conclusion and have it back up maybe some theories that we have. So a model is simply an explanation of why certain events occur and how the data and events are related. So we're trying to have something to represent maybe what we can't see, but have a model to represent that. They may be visual, verbal, mathematical, so anything that helps us understand what's taking place. If we go through all of this process and we're pretty sure that what we're seeing is a repeatable pattern, we could make kind of a broad statement which might be categorized or defined as a theory. It's a broad generalization that explains the related groups of facts or processes. That just means if you feel like after doing several, even hundreds of experiments, you feel like the same thing is happening over and over again, you could probably say this is going to happen all the time, and therefore come up with some theory that would be backed up by your data, a pattern basically, be backed up by your pattern and your experiments. All right, answer question number 3 right here. This flow chart is just kind of showing you the scientific method in a diagram. Please understand that this is not a fixed approach. The scientific method is quite fluid, and it is able to be shifted and moved. So it's not that you have to go lockstep one thing after another in order to be following the scientific method. Scientific method just means you're using your senses to discover things. Okay? So naturally, we are making some observations, and from that we might then draw some conclusions, some early conclusions, often called hypotheses, and then we want to test that. We want to test that and say, is this true? Is what I'm observing really true, or is it just an exception? Is this always going to happen? All right. We then draw some, from all of the experiments, we are going to make a theory and draw some type of pattern from it all, construct some models, maybe make some predictions, and then we might even say, hey, here's what I discovered. And then you can put your information out there and let other people build upon that, and either they can confirm that or refute it, but that way it's out there for everybody to see and everybody can benefit from it. All right, that basically is section 1 of chapter 2, just introducing the scientific method, which I'm certain you are already familiar with. So go ahead and answer these questions in the review section here, and then come back to the video and we'll jump into section 2. Units of measurement in section 2. So the idea here is that we are going to be taking a lot of measurements and collecting a lot of data, and we want to make sure we are very familiar with the units that we use in chemistry. All right? If you were given a recipe and you were told to add a certain amount of the ingredients, but you had no units involved, it would be chaotic. It wouldn't work. So you would need to know whether you're talking about teaspoons, tablespoons, cups, ounces, grams, etc. You got to know. You have to know the units. A value is incomplete, even wrong, I might say, if you don't have the units. All right? Anytime you take a measurement, you're going to have a value and you have to put down the units. It is a must. So a quantity is something that's going to have magnitude, size, or amount. And anytime we measure a size, the amount, the magnitude of anything, we have to make sure that we have units attached to it. Those units basically are, they're man-made units, understand. The units of measurement compare what is measured to what has previously been defined as a certain amount, defined by the scientific community. Okay, these are universally accepted values that can be applied anywhere in the world. We standardize those different units, and often the scientific community uses what is called the SI units. So scientists have agreed on a single measurement system. You have to agree. Everybody has to use the same measurement system, otherwise there's just going to be too much randomness and chaos and confusion. So that single measurement system that is used in the scientific community is called the SI unit. It actually comes from French. It is Le Système International d'Unité. So in English, it's the System International. Okay, the international system, but in French, it's Le Système International. Okay, and basically there are 7 units that we call the base units. Those base units are the foundation of measurements in chemistry. Let's look at them. And before we do, you can answer that critical thinking question right there. Nope, we just did this here. Sorry, here we go. All right, the base units are for the different quantities. You'll see the quantities here on the first column, and then the symbol that is associated with that particular quantity, the name of the SI unit, the abbreviation, and then how it is defined or how it is standardized. What you need to be really concerned with, and what we're going to be using most, is length, mass, time, temperature, and amount of substance. I also want you to be familiar with electric current and the luminous intensity, but those are going to be not used as frequently in this course. So you need to know what the symbol is for each of those. You need to know what the name is for each of those, and you need to know the abbreviation for those units for each of those. You don't need to know how they are defined or how they are standardized. You just need to know basically the quantity symbol, name, and abbreviation. You're going to become very familiar with them as you use these throughout the course. I want you to take some time right now and answer this critical thinking here. You'll notice that there is a big table, and it is telling you the prefixes. Those prefixes are going to be used very, very frequently in this course. Those prefixes are telling you a certain power of 10. So for example, if it says kilo something, like a kilogram means, the kilo prefix means 10 to the third. Okay, that's because a kilogram is 1 times 10 to the third grams. 10 to the third is equal to 1,000, right? So it's 1,000 grams. Or a kilometer is 1,000 meters. So you need to be familiar with these different prefixes here because they're telling you powers of 10. And those prefixes are used in the SI unit measurement system. There are some blanks here, so you're going to fill in those blanks and then become familiar with these prefixes. So these prefixes are used in order to indicate larger or smaller quantities. So you'll notice right here that below this row, these values are smaller. You're getting powers of 10 that are negative powers here. And above this, these are all going to be greater, larger values than the SI base unit. Okay? These are great examples over here. I would encourage you to look at this column here that shows the examples, and it'll make a little more sense to you. I think I've mentioned this before, maybe in the previous video, but it is important for you to understand the difference between mass and weight. So mass is just the amount of stuff, the amount of matter in an object. Weight is totally dependent upon the force that is pulling on that matter. So mass does not change if you were to take an object and move it from one place to another place, assuming you haven't removed anything or added anything to that object. So the mass is less variable, doesn't vary as much as weight does. Weight can vary because it depends on the force of gravity that is pulling on it. You go to the top of a mountain, very tall mountain, the pull of gravity is going to be different than if you were to go closer to the center of the earth. The pull of gravity is going to be greater. It's going to be less at the top of the mountain. So you're going to have a difference in your weight, but not a difference in your mass. You go to the moon, you can have a difference in your weight, but not in your mass. Okay, length. The SI unit for length is meter. You have to be very familiar with that. And kilometer would be 1,000 meters. Okay, try these two practice problems here, A and B. If we take SI base units and we combine them, meaning we take two or more SI base units and we combine them, we get what's called a derived unit. Derived means it originated from the SI base units. Okay? So derived units are formed by multiplying or dividing one or more of the SI base units. So for example, if you want to find area of something, area of a rectangle, for example, is length times width. So length and width are both measurements of distance. So you would have meters, this would be in meters, and the width would be in meters. And when you take meters times meters, you're going to get meters squared. How many square meters? So meters squared is a derived unit because it is using, in this case, meters twice. It's using the base units there, the SI base units, and you're multiplying or dividing them. Here's another one. A Newton. A Newton is used for force, and the measurement or the units for a Newton is kilogram meters. You take kilograms, mass times distance, divided by time squared, in this case second squared. So it's kilograms meters divided by second squared. There's 4 different SI units that are involved there. That's a derived unit. Okay? Joule. Joule is used for energy. Energy is a Newton, we just talked about Newton, times meter. So that would be a kilogram meter times another meter, so it would be meter squared, over second squared. That's energy. In short, though, it's just called a Newton. Here are some more derived units. So you need to become familiar with these as we work through the course. Area, volume, density. Molar mass, we'll talk about what a mole is in this class. Molar volume, energy. All right, those are some examples of derived units. Let's talk specifically about this derived unit, volume, and it is the amount of space occupied by an object. If we're using meters, then it would be meters cubed when we're talking about volume. In other words, you're trying to figure out how many cubes, and that cube is 1 meter by 1 meter by 1 meter. How many of those cubes are going to fill the space that you are talking about, that you're looking at? So, if you need to convert volume in a particular unit to volume in another unit, for example, if you wanted to find out 1 cubic meter, that's pretty big. That's 1 meter is about 3 feet. So that is a box that is 3 feet by 3 feet by 3 feet. That's a pretty big box. And you're trying to find out how many little tiny centimeter cubes would fit into that. 1 centimeter by 1 centimeter by 1 centimeter. To do that conversion, you have to multiply by the unit multiplier. This is called a unit multiplier right here. In this case, there are 100 centimeters in a meter. There are 1,000 millimeters in 1 meter. But we're talking about centimeters right now. 100 centimeters in a meter, and you would have to multiply by this unit conversion 3 times. Why 3? Because meters cubed means meters times meters times meters. So you know how to set up your unit multiplier. This is a unit multiplier because this is equal to 1 unit. 100 centimeters and 1 meter are equal to 1. You're just multiplying by 1 3 times, but you're doing it in a way that the units are going to change. Whatever unit you are starting with, that is the unit that goes in the denominator. And the unit you want to end up with is in the numerator. So you have meters cubed, so you have to multiply by meters cubed, which means you have to multiply by you have to divide by meters 3 times. And you want to go to centimeters, so you put the equivalent value in centimeters up above in the numerator, and this tells you to go from meters cubed to centimeters cubed. I have to multiply by 100 3 times. Okay? You end up getting 1,000,000 cubic centimeters. For example, here's another one, liter. It's not an SI unit, by the way. The liter is equivalent to 1 cubic decimeter. A decimeter is not even an SI unit. Okay, it would be the meter, but you could convert it to cubic meters. There are 10 centimeters in a decimeter, and we could take that liter and we could convert it to centimeters cubed, and there would be 1,000. Okay, again, we're going to have to get very comfortable with converting from one unit to another unit, and we'll do some practice with that. All right, go ahead and answer this reading check number 4 here. Here's some examples of some different measurements for volume. So a liter, there's a cubic centimeter, there's 1,000 cubic centimeters. There's your 15 milliliters. Milliliters we often use in chemistry whenever we measure volume, like for liquid. All right, here's another derived unit often used in chemistry, density. Density is mass over volume. So M is for mass, V is for volume, and so whatever the mass is measured in, let's say it is measured in kilograms. And your volume, if it's measured in cubic meters. Okay, you could have the density measured in kilograms per cubic meter. Or it could be measured in grams per cubic centimeter. So whatever the mass is that you're using, whatever the units for the mass, and whatever the units for the volume are, you divide those, and you take that mass that you measured divided by the volume, and you would find the density of that object. And the units are always going to be the units for the mass, maybe grams, over the units for the volume, maybe cubic centimeters. Remember that density is an intensive property. That means that density number is not going to change. Doesn't matter how much of the substance you have. The density for water, pure water, is 1 gram per cubic centimeter. Always. Doesn't matter if you have a gallon of it or a complete lake of it. Doesn't matter how much you have. It's always going to be 1 gram per cubic centimeter. The nice thing about that is that you can use density to identify a substance. If you're able to find the density of a particular liquid, for example, and you find it to be really close to 1, then it's probably water, or at least mostly water. So as I mentioned, density of water is 1 gram per cubic centimeter. If you wanted to identify another liquid, like, hey, is that mercury? You would test its mass over volume and see if it is close to the known density of mercury. Okay? So, as said, densities are specific to that particular substance, and it doesn't change, and it is an intensive property, means it doesn't matter how much you have, so you can use it to identify different objects. So we know the densities of these different objects here, and if we were to find the mass and divide by the volume, maybe in grams per cubic centimeter, you'd be able to identify what type of substance you have. There's just a chart showing some different densities. Okay? Let's walk through this sample problem together. Here we're actually going to be doing some calculations, so take out your calculator. You always have to have a calculator in this class. We're going to be doing lots of calculations, lots of mathematics, and show you how to use it in this particular problem. So let's say you have aluminum metal. It has a mass of 8.4 grams. The volume of the sample is 3.1 cubic centimeters. They're actually giving you right here the mass and the volume. Okay? You want to find the density. I highly suggest that you start with the known formula for density, and then in place of that mass and your volume, you're going to plug in those given values with the units. Don't forget the units, please. Then take your 8.4 divided by 3.1, get your value, and write the units as well for the density. Okay? Also, make sure that your answer makes sense. Just look at your values up here, 8.4 divided by 3.1. You could start just with a guess, 8.4, that's close to 9. If I round it up to the next number, it's 9 is about 3, so 9 divided by 3 is about, or 9 divided by 3 is 3, which is, you'll notice, close to 2.7. Okay, so just make sure it makes sense and before you move on. Okay, try practice C. You'll notice you are given volume, mass. Try D. This time you're given the density and you're given a volume. So realize here that this time you're given the density. In our formula, D equals M over V. You are given this value. You're given the density and you're given the volume. You're given this value, and you need to solve for mass. It says, what is the mass? So if I was to rearrange this formula, if I multiply both sides by volume, notice volume will cancel here, and I'll have mass is equal to density times volume. So you could rearrange that formula and have it solve for mass, and now just plug in your density and your volume, and you're good to go. Don't forget the units now. Mass, when you do this, your density is going to be grams per cubic centimeter. Your volume is going to be in cubic centimeters. Those are going to cancel, and you're going to have just grams as your units. Also for E, you're given the volume. Sorry. It's asking you for the volume. My apologies. And you're given the mass, and you're given the density. So you're given the density and the mass, this time you're asked to find the volume. I'll let you figure that one out, okay? I did mention this before. I called them unit multipliers. They're also called conversion factors. So these are ratios that basically are showing the relationship between units, but they're unit multipliers because we're going to set it up so that the ratio is really equal to 1, okay? So for example, if you want to convert from dollars to quarters, you would use 4 quarters over a dollar. You would multiply by 4. But if you wanted to convert from quarters to dollars, you would multiply by 1/4 or divide by 4. If you want to go from, here's another way to do it, same thing. You could go, this here is going from quarters to dollars, but it's just, instead of 1/4, you're multiplying by 0.25, same thing. Or here, instead of multiplying by 4, you're going to divide by 0.25, okay? But you have to just look at the units in order to know how to use that unit multiplier or conversion factor to go from one unit to another unit. If we ever come across something called dimensional analysis, it just means that we are using a mathematical technique that allows you to use units to solve problems involving measurements. Okay? So dimensions, when we talk about dimensions, units, dimensions, those two words are interchangeable. So units, dimensions, we talk about meters, centimeters, gallons, those are all units, also called dimensions. Okay? Alright, so for example, if you wanted to convert from dollars to quarters, simple, right? I know it's simple, but it's just showing you how to set it up. So if you had $12, you would be able to use a conversion factor or unit multiplier to go from dollars to quarters. You are going to put dollars in the denominator and quarters in the numerator, and then write in the values that make them equal. There are 4 quarters in a dollar, and this tells you to go from dollars to quarters, you are going to multiply by 4 and get your answer in quarters. Done. All right, you try F and G here. Practice those. This is just saying that conversion factors, you can determine, you can come up with those conversion factors if you just look at the prefixes, and then you'll know how many of one unit equal the other unit. So for example, if you see deci, a decimeter, it means a tenth. So that means there are going to be 10 decimeters in a meter. So just by looking at the prefixes, that will help you know how to set up your conversion factor. Okay? Okay, H says write at least 2 more conversion factors for meters and decimeters. All that means is, if we look here, they gave you 1. 10 decimeters is equal to 1 meter. So we could also write that 1 decimeter is equal to 1/10 of a meter. Now if you flip it, let's say you had to convert it the other direction, then we would say that 1 meter is equal to 10 decimeters, or you would say 1/10 of a meter and 1 decimeter. So these two basically are saying the same thing and will help you convert from meters to decimeters. These two are saying the same thing and will help you convert from decimeters to meters. Okay? You can do this one. You want to go from seconds to minutes, use my example right up here at H. Okay, this sample problem here says determine what information is given and unknown, and it says express a mass of 5.712 grams in milligrams and kilograms. We're just going to convert. Realize we're not changing the mass. The mass is still the same. We're just changing the units. So that's why the value is going to change, because we're changing the units. But the mass itself, the matter, is not changing. We're just using a larger or smaller unit. So we're given a mass of 5.712 grams, and we need to find out what that is in milligrams and in kilograms. Now, milligrams is a prefix that is telling you the unit, the size of the unit is smaller than a gram. It's a thousandth of a gram. And a kilogram is telling you the unit is bigger than a gram. Okay, it is actually 1,000 grams. A milligram is a thousandth of a gram. A kilogram is 1,000 grams. So just by looking at the prefixes, which we looked at before, and you will memorize those, you will learn those. 1 gram is 1,000 milligrams, and 1,000 grams is 1 kilogram. So if we wanted to convert grams to these two, we are now going to use those two conversion factors that we just derived. So we're going to take our known mass, and since we want to cancel grams, grams goes in the denominator. 1 gram is 1,000 milligrams. So the grams are going to cancel. We're going to end up with milligrams, and we know that we're going to multiply by 1,000 to get our value in milligrams. Whereas for kilograms, again, we want to cancel grams and go to kilograms. 1 kilogram is 1,000 grams. So if we want to cancel grams and go to kilograms, this tells us we're going to divide by 1,000 in order to get our value in kilograms. Okay? Again, make sure it makes sense. Okay, here are some practice problems. I'm going to let you work on these. It sets it up for you very nicely here. Very suggested, a very nice way to set these up, and I suggest you do it, is write down what is given, that would be this, and write down what is unknown, that would be the length in centimeters. Find out what the unit multiplier is, or the conversion factor. Write those, choose which one you need to use, and then finish the problem. Okay? You can do K and L as well, and I'll check those when you submit it. Then you've got the 2.2 review section here. Go ahead and work through these problems, applying exactly what we just talked about, everything in 2.2, and work through each of those problems, and then I'll send you the answers after you've submitted it for me. Okay, section 2.3, we're going to talk about these scientific measurements, but not just introducing them to you. We already did that in the previous section, but how are we going to use them? Okay? Often when we make measurements, because maybe our instruments are not very good, or maybe there's human error, maybe two people are making the same measurement but they get different answers. You may make the same measurement twice, but the result is different. Maybe it's different the second time. All right? It doesn't necessarily mean that a mistake has been made. It just means that the measurement may not be the best. Maybe the measurement tool is not the best. So our reliability goes down as a result, and so we have to be aware of that in science. Okay? We have to be aware of that, that factor, that influence. So anytime we are making a measurement, we are very much aware of two things: accuracy and precision. Let's define the two, and let's talk about how they are different, because we often use those words interchangeably, but they're actually different. So, accuracy refers to how close the measurement is to the correct or accepted value. Okay? So I mentioned before that the density of water is 1 gram per cubic centimeter. If I was to give a group of students a glass of water, and they measured the mass of it and calculated the volume, and they got answers that were way off, they got 5 grams per cubic centimeter, they would not be very accurate. If students got something close to 1.1, 1.05, or even 0.9 or something like that grams per cubic centimeter, pretty accurate. Okay? How close are you to the accepted true value? Precision has to do with something, a measurement that you're going to repeat over and over and over again. Precision really is telling you more about the instrument that you're using and the method of measurement that you're using. Okay? Because precision refers to how close a set, notice a set of measurements, a group of measurements, a whole bunch of measurements. How close are those measurements to each other? Were you able to repeat it and get the same answer, or almost the same answer, again and again and again and again and again? That's precision. Okay? And really it's largely dependent upon the instrument. A ruler that has lots of tiny little marks on it is going to be more precise than a ruler that only has a few marks on it. So this ruler here is less precise. It's harder to make a measurement that's going to be exactly the same every single time if there are not very precise marks on that instrument. All right? Now, when we take a measurement, our measurement could be accurate. A particular measurement could be accurate, but it could be not very precise because we have multiple measurements and they're all over the place. Or it could be precise but not accurate, or it could be both, or it could be neither. Okay? So measured values that are accurate are close to the accepted value. Measured values that are precise are close to each other. Let's look at the dartboard right over here. Right here, you throw 4 darts. 1, 2, 3, 4, and they all are really close to the bullseye. So the bullseye is like the accepted value. That is the desired result. All of these darts are really close together. They're precise, and they are close to the bullseye, the target. They are accurate as well. Okay, they're both high precision, high accuracy. If you were to throw darts, and let's say you do not get close to the target, you're way off from the desired result, the accepted value. They are not very accurate, but for some reason, they're all close together. Okay? So they have high precision. You're able to repeat it over and over and over again and get the same results. If this happens, that might tell you, hey, there's something wrong with my instrument. My instrument is off, or my measuring technique is off. Okay? Because I got the same results over and over again, but they're way off from what I think it should be, or what I know it should be. Okay? All right, so now you can answer the difference between accuracy and precision. So again, here's a set of darts. As mentioned before, if all the darts are close to the bullseye, you're going to have high precision and high accuracy. In this case now, though, you are going to throw the darts, and those darts surround the target. Now, often in chemistry, we do several measurements, and then we take the average of those measurements, because we know the measurements are going to be off a little bit. High, too low, a little bit, surrounding, if you will, what we believe to be the correct answer. So we do the average. Now, if I take the average, the spatial average here of these darts, you'll notice these darts are all surrounding the accepted value, the target. So on average, the 4 of them kind of have the target contained. Okay? They're centered around the bullseye. So although not a particular one hit the bullseye, all of them are surrounding that bullseye. So on average, you would say, well, this one's a little too far to the right, but this one's too far to the left. So they cancel each other out. This one's too far up, this one's too far down. But on average, they all came around that target. But they have very low precision because one is way to one side, one is too high, one is too low, one is too far to the left. So it's very low precision, very unpredictable as far as repeating it over and over. Okay? All right, you can answer this critical thinking. It says apply here. Imagine you throw 4 darts and you want both, you want to be imprecise. That means very low precision, and inaccurate, low accuracy. draw here 4 darts that would fit into those two descriptions. Because we know there's going to be error in our measurements, we're going to calculate something that is called percent error. We want to find out how far off are we. Are we way off, or are we just slightly off? And percentage error allows us to do that. So percentage error, to calculate the percentage error, here's what you do. You are first going to subtract the accepted value and your value. So you're going to take the experimental value. This is from the measurement. This is your value. This is your value that you calculated, that you measured, and subtract the accepted value. The accepted value would be like the value that is the actual value that is believed to be for whatever you're trying to measure, okay? And then you're going to take that difference. Actually, you should probably take the absolute value of that so that it's not negative. We just want to find a positive percentage error, and then divide by the same accepted value, and then multiply by 100 in order to get a percentage, okay? So you don't have to take the absolute value. You can take, you can have it be positive or negative. If you get a positive percentage error, that means your value is higher than the accepted value. If you get a negative percentage error, that means your value is lower than the accepted value. Okay? You can do number 3. Sample problem. Student measures the mass and volume of a substance and calculates its density as 1.4 grams per milliliter. The correct or accepted, the true value is 1.30. What is the percentage error? So here's what we're given. We're given the measured value, we're given the accepted value, and we want to find the percentage error. So using our formula right here, plug in our numbers. This is the student's measured value. This is the true value, the actual measurement, what it should be, divided by that accepted or true value, multiplied by 100, and they get 7.69. Okay? So they're off by less than 10%. That's not too bad. Okay? Not too bad. You can now do A and you can do B using the example up here as a sample. Now, as we mentioned, there's always going to be error in measurement. Okay, our measuring tools are not perfect, and us as humans are not perfect. So there's going to be some error. There's always going to exist error and uncertainty in any measurement. Okay. So, and that, as I just said, that's because of the measurer, and it's also because of measured instruments. There are limits to how precise we can be. All right, so as I mentioned before, a ruler that has lots of marks on it, you can make a measurement that is more precise compared to a ruler that doesn't have very many marks on it. So you can be more precise as far as the length of this nail. If your ruler has very fine, small marks on it, we can take that measurement out to a further decimal place than if there's only marks every centimeter, for example. Okay? That's what this is saying right here. Now, when you measure, you are always allowed in a science to measure to a decimal place where your last decimal value is a guess. Here's what I mean. This ruler right here, you know that this nail is longer than 6 but shorter than 7. That is guaranteed. You know that. Also, everybody would agree that the nail is longer than 6.3, but shorter than 6.4. Everybody would probably agree that it's between 6.3 and 6.4. Now here's where the differences lie. Some students, some people that measure this say, well, I get to guess now. I get to guess one more value. You're allowed to guess one more value after the however many you are certain of. So I would say, well, I think it's right in the middle. So somebody might say it's 6.35. Somebody would say, no, I think it's actually 6.34. Somebody might say it's 6.36. All of these are valid measurements. Okay? So you are allowed to measure with whatever instrument you have, and that instrument is going to determine how precise you can be. You are allowed to have a measurement such that the last value you are actually guessing. Not two values, only the last value you can guess. The other values you have to be certain of. All of the values that go into this measurement are called significant digits or significant figures. Okay? So those figures are those that are measured precisely, plus one estimated digit. All of those are called significant figures. And those significant figures, how many significant figures there are going to be, depends on the instrument that you're using to measure whatever you're measuring. Okay? So in science, measured values are reported in terms of significant figures. Significant figures are all of the digits known with certainty, all of those values that everybody would agree upon, and then the last digit is one that you estimate. And there might be some differences as far as what that last digit should be. The final digit is an estimation, and you're allowed to do that. And all of those are going to be significant digits. Okay? So just as I mentioned before, the length of that nail, somebody might say it's 6.36. Somebody else might say, no, it's 6.35, 6.34. Okay? So when we say significant, we don't mean that it's certain, like that last digit we know is not certain. It just means that it is part of the accepted measurement that is going to be reported. Okay? All right. How do we determine whether the digits are significant or not? Well, determining the number of significant figures is important. If a measurement does not have any digits that are zero, all the digits are considered to be part of that valid measurement and are significant. Okay? So 6.36, all three of those digits are significant and are part of that measurement according to the precision of that instrument. But if there are zeros involved, this is where it gets a little tricky. Okay? The zero could be significant or it may not be significant. It depends on how it's being used. Okay, let's talk about this. Now this looks complicated, but really the only thing you have to worry about as far as determining whether it's significant or not would be the zero. Okay, that's the only thing that is a little bit tricky. Anything, any other digit, 1, 2, 3, 4, 5, 6, 7, 8, 9, those digits are always significant. Okay, so these rules all tell you when a zero is significant or when it is not significant. Okay, here is when a zero is considered part of the measurement and is significant. If a zero is in between two non-zero digits, like this zero and these two zeros, then they are part of the precision of that instrument, and they are significant. So this value has 3 significant figures. This one has 5. But if the zeros are only there as placeholders, I repeat, if they're only there so that all the other digits get moved to the right location, then those zeros are not considered as part of the precision of the instrument. So it says zeros that appear in front of all non-zero digits are not significant. These two zeros are there so that the 9, 5, 8, 9, 7 are in the correct location. They're not there because they are really part of the measurement. That's not important. These 4 zeros are just placeholders. So those zeros that are simply there to take up space are not considered significant. This number has only 5 significant digits. This one has only 1. If the zeros are at the end of a number or I should be more specific, if they are after a decimal point, then that means they were used as part of the precision of the instrument. You are measuring out to the nearest hundredth of a gram here. You are measuring out to the nearest, wow, whatever that is, okay? 10, hundredth, thousandths, 10,000, 100,000, millionth, 10 million, 100 million, billionth of a millimeter, okay? Zeros at the end of a number and to the right of a decimal point are significant. 4 significant figures. This one has 3, 6, 9, 10 significant figures. Okay? All right, last rule for the zeros. If the 0 is at the end of a number, there is no decimal point. These 3 zeros right there are simply taking up space so the 2 can be in the right location. Those are not significant. Okay? Not significant. The only difference would be is if there is a decimal point at the end. That decimal point makes all the difference, because here that decimal point is saying I am measuring to the nearest unit. I think it is exactly 2,000. But this measurement up here is saying I only am estimating to the nearest 1,000. I think it's around 2,000 meters. This is saying I think it's exactly 2,000 meters. So if there's no decimal point, those 3 zeros are not significant, and this only has 1 significant figure. This one, though, with the decimal point at the end, 4 significant figures. Okay? All right. Here are some great practice problems for you. You have to figure out, determine the number of sig, I might say sig figs, by the way, sig figs for significant figures. How many sig figs? Determine how many sig figs. Okay? And suppose the value 7,000 centimeters is reported to you. Ah, yes, you can do that one. You want to write it so there's 1 sig fig, 4, or 6. Okay? So go ahead and work on those and then come back when you're ready. When we round, we want to be able to round up or down or round off in order to have the correct number of sig figs. So anytime we add, subtract, multiply, or divide 2 measurements, the reliability of the result should be reflected by its significant figures. Here's what I mean by that. If you have 2 measurements and one measurement was more precise than the other measurement, if you then add or multiply or divide or subtract those 2 measurements, your result cannot be more precise than the least precise instrument that was used in any of the measurements. Okay? So, here's what you need to know. When you are adding or subtracting any numbers in this class, we need to figure out how many sig figs the answer should have. And here's how you determine it. The first measurement in this example here, we're going to take 25.1 and add 2.03. The first measurement has 1 digit to the right of the decimal point, and the other value, 2.03, has 2 digits to the right of the decimal point. So if we add 25.1 and 2.03, you'll notice that this first measurement is taken out to the nearest tenth. This second measurement is taken out to the nearest hundredth. But our answer cannot be left to the nearest hundredth because we used an instrument over here that was only accurate or only precise to the nearest tenth. So our answer has to be rounded off to the nearest tenth. So if you take 25.1, and you add 2.03, yes, of course, you're going to get 27.13. But you are then going to have to realize I can only have this answer to the nearest tenth because that's what this measurement was. I can't have it to the nearest hundredth. My answer can't be more precise than my least precise measurement right there. So I look at my 1, I need to round to the nearest tenth. I look at the number behind it, it's a 3, it's less than 5, so I round to 27.1. Okay? That's the same thing with subtraction. You can't have it more precise than the least precise measurement. So whatever the least precise place value is, that's what you have to round off to. Now with multiplication and division, it's a little bit different. So with multiplication and division, if you take your calculator and you take 3.05 and divide by 8.47, your calculator doesn't know about sig figs. It's not as smart as you. So it's going to take your answer and give you way out to, this place value, way out there. But that's way too precise. You can't give me that answer and say, I am certain that the answer is 0.3600944451. You can't, because up here, you were measuring only to the nearest hundredths. You had 3 sig figs here, you have 3 sig figs there. Your answer can only have 3 sig figs. Okay? Don't look at how many decimal places. That's only for addition and subtraction. Up here, you look at how many decimal places there are. But here, you look at the number of sig figs. So I have to round this off to only 3 sig figs. Okay? The answer can have no more significant figures than the measurement with the fewest sig figs. So I would have to round this to 0.360. All right? Now, if you look at these rules for rounding, you're probably familiar how to round, but if the digit following the last digit, if it's greater than 5, then you round up, like that example. If it's less than 5, then you are going to round off, like that example. In this case, this is saying basically that if you are rounding this to the nearest hundredth, and it's followed by 5, that's okay. So it's going to round up to 0.79. But I don't care about these two rules down here. Okay, so don't worry about those two rules. Let's just say if the number that follows the one you're trying to round up or down is 5 or greater, then round it up. If it's less than 5, then round it off. Okay? This is some summary of the rules for addition and subtraction when it comes to sig figs. So this is how you would know how to figure out how many sig figs your answer should have. Here's some great examples right here. You should study these and make sure you understand why those examples are the way they are and why your answers here have the certain number of sig figs that they do. Okay? Same thing here. These are great examples for multiplication and division. Notice all of these answers do not have more sig figs for multiplication and division than the least number of sig figs in either of your measurements. This has 2 sig figs. That's because this only has 2 sig figs. This has 2 because that only has 2. Okay? Now, there is one thing that you don't have to worry about, and that is when you are given exact values, you don't have to worry about the sig figs in those exact values. Okay? So conversion factors, they don't have any uncertainty, so you don't have to worry about those when you're thinking about sig figs. Right? They're exactly 100 centimeters in a meter. That's a man-made system. Okay, we say exactly. Those are exactly how many. That's not a measurement. That is a system that we created. Okay, so you don't have to worry about certainty or uncertainty when you're using values that are exact. Okay. Also, if you count 10 test tubes, that's an exact value. You don't have to worry about how many sig figs are in that exact value when you're counting something or using conversion factors. All right. Go ahead and do these practice problems here. Practice those, and you can check them when I send you the answers. Okay, let's talk about one more thing that is often used in science, and that is a form of a number that is called scientific notation. So hopefully you're already familiar with this. This will be a review. Scientific notation just writes the number in a different form. It doesn't change the value, just in a different form, so that it is written as something times the power of 10. Okay? Large numbers are going to have positive powers of 10. Small numbers are going to have negative powers of 10. It's probably easiest just to show you some. Hopefully you're already familiar with this. This is a small number. And if I want to write this as something times 10 to a certain power, I know that this decimal point, every time I move it, it means also either multiplying or dividing by 10 to get back to the original value. So all I do is I move this decimal point until 1, 2, 3, 4, until I have a number between 0 and 10. Actually between 1 and 10. Okay? So the number's got to be between 1 and 10. So if I move that decimal point here between the 1 and 2, I get 1.2. And this is a small number, 0.00012. I move the decimal point 1, 2, 3, 4 places. So I know that if I take 1.2 times 10 to the negative 4, I will have exactly the same value that I started with. It's just now written in a different form called scientific notation. Anytime you multiply by a power of 10 that is negative, like negative 4, it means you're dividing by 10. 1.2 divided by 10 4 times gives you that same value right there. This is a very large number. The decimal point is at the end. It's not written, but it's at the end. 1, 2, 3, 4, 5. And I get 5.6. So I moved it 5 places until I get a number between 1 and 10. 5.6 is between 1 and 10. I can't stop between the 6 and 0. I give me 56. That's not between 1 and 10. I can't go past the 5. That's 0.56. That's not between 1 and 10. Now I got times 10 to figure out what the power of 10 is. I count how many times I moved that decimal point. 1, 2, 3, 4, 5. It's a big number. So 5.6 times 10 5 times gives me that same exact value. Different form, same value. Okay? We can go from scientific notation to standard notation, or they call it ordinary notation. So you just take 7.050 times 10 3 times. Every time you multiply by 10, the decimal point moves. If you multiply by a power of 10, it moves to the right. If you divide by a power of 10, it moves to the left. So this is going to be 7.050. I moved it over 1, 2, 3 places because I multiplied by 10 3 times, and I get 7,050 grams. Finish those up. Finish all these other problems. Okay? Okay, I'm going to let you read through this on your own because it's showing you addition and subtraction using scientific notation. So you need to become familiar with how to do that, and it shows you maybe how to do it using a scientific calculator. Okay, but hopefully you're familiar with this mathematics. It gives you an example right here. You can look at that example and conclude on your own how you can easily add and subtract when a number or numbers are in scientific notation. Same thing with multiplication and division. It's easy to multiply numbers that are in scientific notation because you multiply the numerical part and you add the powers of 10. You add the exponents on the tens. So here's some practice. I would encourage you to practice this without a calculator and then maybe verify with your calculator. Okay, I'm not going to spend a lot of time here. This is just showing you that when you have problems, there's a systematic approach to solving those problems. First, you want to analyze, okay, read the problem carefully. You might even have to read it twice. Gather in the information, devise a plan. What are you going to do in order to try to attack this certain problem, and then solve it, and then check your work. Okay, again, you probably already do that, but you do want to have a systematic approach. So reading analytically is very important, and then try to come up with the given information, the unknown, the known and the unknown, okay, and use that then to point you maybe to a correct formula or a correct method, and then try your approach and make sure it makes sense. Okay? I'll let you answer reading check number 6 right there. So here's where you're going to, you notice there, I want you to apply the analyze, plan, solve, and check your work. So this is a problem where you are finding the volume when you know the mass and the density. We did one like this before, so I'll let you read through this and see how they're setting this up, which is very methodical, very systematic, and very good, by the way. Okay? You'll make less mistakes if you are careful in setting up your work. Okay? You can practice L here, and you can use exactly the same method. See how well they set it up. Use your approach here in order to get the correct solution, and then make sure your answer makes sense. Okay, we're getting near the end here, and we're looking at relationships. As I mentioned before, when we take measurements, we're looking at those measurements and trying to determine relationships. Well, there are important relationships here, two of them which we're going to talk about right now. Two quantities that are directly proportional. What that basically means is that when one goes up, the other goes up. So if you have item X and item Y, and X and Y are related in some way, they're related in a direct proportion if when X increases, Y also increases. They don't have to increase by the same amount, but if they both increase, when one increases, the other increases, that's a direct proportion. Or if when one goes down, the other goes down, that's a direct proportion. That relationship is described mathematically by writing it one of two ways. You can say that y over x, meaning the ratio here, the ratio is going to be a constant. So that just means that, let's say y goes up, well, x has got to go up too in order to keep this ratio the same. Or you can write it as y equals kx. Now this is actually a linear. It shows you a linear relationship. You may be familiar with y equals mx plus b. Well, that's what this is right here. There's your y equals mx, y equals kx. All right? So a linear relationship means as one goes up, the other goes up. As x increases, y increases, and we get a linear relationship, or a direct proportion. Here's an example, mass versus volume. This is an example. Here's a bunch of numbers that were collected, measured. So here's a mass and volume, and then the calculated density. These masses and volumes are then plotted. Here is the volume on the x-axis, the mass is on the y-axis. They take this number, 20.1, and the 54.7, and they plot that point right there. And they do that for all five different points, 5 sets of points there. And they get these 5 points right there. And when you draw a line through those, or you draw a line that represents that all these points, doesn't have to go through all of them, a line of best fit or a trend line, you'll see that we have a linear relationship. So that means that mass and volume are in a direct relationship. Okay? So you guys know you know that density is equal to mass over volume. Well, if we solve for mass is equal to density times volume. There's your m equals dV, or m equals kV, or y equals mx. You know, that's your linear relationship right there. Okay? All right, the other relationship would be an inverse proportion. What that means is that when x goes up, y goes down. They go in opposite directions. Again, not necessarily in the same amount in opposite directions, but they're going to be inversely proportional. The relationship here is that y times x is going to be a constant. So the product is going to be a constant in this case, not the ratio. Or if you solve for y is equal to some constant over x. All right? So in this case, here's an example. You collect all this data, And again, you plot all of these different points, you'll see that as pressure increases, volume is going down. Not necessarily in a linear relationship, not necessarily linear. This is not a line, but this is going down here. Volume is decreasing as pressure is increasing. That is an inversely or indirect relationship. Okay? All right, right here you've got 2.3. That was kind of a long section. You can look at these review questions, answer all of these, and once you're done with that, along with everything else, you can submit it to me and I will send you the answers. And then don't forget the Chapter 2 review here, which is going to be a nice set of questions to help you encapsulate and review the entire chapter, to put all those pieces together and help you kind of bring it all together at the end. So spend some time answering those questions, and then let me know if you have any questions about any of these, either before or after you get the solutions. Okay? All right, let's keep working hard, and as I said, don't hesitate to let me know if you need any assistance.